All right, let's get into it. Today, we're basically becoming scientific detectives. We're going to uncover this hidden power structure that rules the entire world of metals. We're about to find out why some are, total chemical superstars, while others, yeah, not so much. So it all kicks off with a really simple question, one you've probably wondered about yourself. How come an iron nail you leave outside turns into a pile of rust, but a piece of gold jewelry from like an ancient tomb can look brand new after thousands of years? Is it just that gold is tougher, or is there something much deeper going on?
Well, the answer is there's a hidden hierarchy. It's like a secret power ranking that every single metal fits into. And our mission, right here, right now, is to follow the clues from a few key experiments and uncover this ranking for ourselves. Let's do it.
Okay, every investigation needs a starting point, and ours begins with our very first clue. How do different metals react with something as simple as the oxygen in the air? Now, we're going to add a little bit of heat just to give them the energy they need to get going, and we're going to watch very, very closely.
And right away, the results are fascinating. Just look at the range here. On one end of the spectrum, you've got potassium, which just goes wild. It bursts into this fierce lilac flame with just a tiny bit of heat. Then you have iron powder, which puts on a pretty good show with these yellow sparks. Copper, way calmer. Its surface just turns black. And gold, well, gold does absolutely nothing. This gives us our first draft of the hierarchy, right? Potassium is clearly at the top, iron's in the middle, then copper, with gold sitting at the very bottom.
So yeah, this just makes the two extremes crystal clear. Over here, you have the super reactive potassium basically throwing a party with colored flames. And on the other side, you've got completely stable, unbothered gold, which won't react no matter how much you crank up the heat. We've definitely found the top and the bottom of our list. All right, clue number 1 is in the books. For our second clue, we're upping the ante. Air was a good start, but now we're going to move on to a tougher test, the water challenge. This should really help us figure out where those metals in the middle actually belong. You see, with water, we can get way more specific. The most reactive metals, they'll just go for it in plain old cold water. Others, though, they need a bit of a push. They need that extra energy from hot steam to get going. And some, as we've already guessed, probably won't do a thing. And boom, the results give us another huge piece of the puzzle. Just look at potassium. It reacts vigorously with cold water, fizzing away and spitting out hydrogen gas. Calcium does the same thing, just a little more chilled out. Now, magnesium is where it gets really interesting. It doesn't do much in cold water, but hit it with steam, which has more energy, and it reacts. And copper? Nope. Doesn't care about water or steam. Okay, we're definitely seeing distinct groups forming now. So a really clear pattern is starting to emerge from all our clues. It seems like the more energetic, the more violent the reaction, whether it's with air or with water, the higher that metal's rank is in this hidden hierarchy. Our detective work is really paying off. Okay, we've gathered the clues, we've seen the pattern, and now it's time for the big reveal. Let's put all these pieces together and uncover the fundamental science that explains everything we've just seen. The whole secret, the key to this entire mystery, is a property called reactivity. And what is that? It's actually pretty simple. It's just how easily, how readily, a metal atom loses its outer electrons to become a positive ion. That's it. The whole ranking is based on this one single thing. The more reactive a metal is, the more it wants to get rid of those electrons. Think about it like this. A really reactive metal, like our friend potassium, is just incredibly eager to give its outermost electron away. It's barely hanging on. But a less reactive metal, like gold, holds on to its electrons super, super tightly. So every single reaction we saw was just a measure of this chemical eagerness. And all of that leads us to the solution to our mystery, the Metal Reactivity Series. Here it is in all its glory, from the most reactive at the very top down to the least reactive at the bottom. This one list explains everything. Potassium's at the top. That's why it went crazy in the air. Gold is at the bottom, which is why it did absolutely nothing. And iron, right there in the middle, which explains why it rusts over time but doesn't, explode when it gets wet. So we have our series. But this isn't just some list you have to memorize for a test. This is a genuinely powerful tool. If you understand this hierarchy, you can basically predict the future. Well, the future of chemical reactions anyway. Let me show you how. So, what do you think would happen if we took a highly reactive metal from the top of the list and introduced it to a compound that contains a less reactive metal from the bottom? I mean, it's kind of like putting a heavyweight champion in the ring with a lightweight. Who's going to come out on top?
What you get is something called a displacement reaction, and it is exactly what it sounds like. The stronger, more reactive metal literally kicks the weaker, less reactive one out and takes its place in the compound. It's a total power move. The stronger player just subs out the weaker one.
And this slide just illustrates it perfectly. On the left, we take zinc, which is higher up on our series, and we put it in that blue copper sulfate solution. Because zinc is more reactive, it displaces the copper, and you can actually see the blue color of the solution fade away as it happens. But on the right, we try it the other way around. We put copper into a zinc sulfate solution. Since copper is less reactive, it's just not strong enough to kick out the zinc. And nothing, absolutely nothing happens. The series predicted it perfectly. And this brings us to the formal scientific rule, which is a huge takeaway. A metal higher in the reactivity series will displace anyone lower in the series from a solution of its compound. That is the golden rule of metal chemistry. Now, why does any of this matter outside of a chemistry lab? Because this principle isn't just some neat trick. It is the foundation of a massive global industry, how we get pure metals out of the ground. You see, a metal's rank in this series dictates how we get it from its ore. The most reactive metals, like sodium, form these super stable compounds that are incredibly hard to break apart. We have to use a powerful and expensive process called electrolysis to split them. Mid-range metals, like iron, are easier. We can just heat their ore with carbon, and since carbon's more reactive, it displaces the iron for us. And the least reactive ones, like gold, they're so stable on their own that we often just find them as pure elements, just lying around in nature. So, the crucial point here, the big idea, is this. A metal's simple tendency to lose an electron, its reactivity, determines everything. It explains why some metals burn and others don't, why some reactions work and others fail, and maybe most importantly, it dictates the cost and the method we use to build our entire modern world with these materials. It's huge. So we've cracked the code for the metals we use today, but that just leads to a final, bigger question. As we start designing the technologies of tomorrow, for space travel, quantum computing, clean energy, what new hierarchies are we going to need? What kind of properties will the supermaterials of the future have to have? That is something to think about.